So Mallik is the Vice President of Product and Business Development at Syntiant. He has more than 2 decades of semiconductor industry experience, working with diverse applications such as neural network processor, digital signal processing, multimedia, networking systems on chips, and FPGAs. So Mallik, thank you for staying with us.
Thank you. Thank you very much. And it's a real pleasure to be here with all of you. And looking forward to this talk here in Asia, tinyML. We had a summit a few months ago. I had the opportunity to be there in California. We won the tinyML Best Product of the Year award over there, as you can see in the right side over here. So I'm here to talk about how Syntiant can enable more acceleration, more AI at the edge using neural decision processors that we have built, and also in general why we need more neural networks and more AI engines, which are accelerators at the in tinyML. Just a couple of quick corporate things about the company itself. We've been in business since 2017. Our first product was in 2018. So this is based on that, what I mentioned earlier, a new kind of processor. We tried to put as much neural network capacity into that chip, but at the same time, the idea was to make it very, very low power. So that product, our first samples of that were in 2018. We've been shipping that in volume to the point now we are close to almost 20 million devices and 19 million devices shipped, and will probably hit 20 million soon. We've raised $65 million over the last 3 rounds, the last being in 2020 from a variety of venture capital investors, strategics, including Intel, Microsoft, and Applied Materials, Amazon, Alexa Fund, Bosch, and Motorola, and others. And we have also been fortunate to have worked with Amazon and Google. As I mentioned, we worked with initially to get, initially we started with wake words. So we were able to get, good partnerships with Amazon to get Alexa working on it, and then helped us to get into a number of opportunities through that ecosystem. We also won a number of awards over the last few years, including the what I just mentioned, the tinyML, one of the awards we are very proud of, and also the CES award last couple of years, and a bunch of other ones. So, and we have launched now 3 other chips since then. The NDP 120 earlier this year, which is the one which won the award. Then we had the NDP 200 for vision, and another chip called for sensing. So I'll talk about that in a few seconds. This chart just shows that we have a big presence in Asia. We've been founded and located in Irvine, but most of a large number of our team is in Asia as well, in India, China, Singapore is operations, and South Korea for sales, and other countries. So now let's jump into what is driving tinyML. What is the force that is pushing? Why did we get this growth? And how is it possible to get that similar growth for others in the industry? Because there's a large opportunities, as we had mentioned earlier at the meeting. So it's the applications are vast and going all the way from mobile, from phones to laptops, computers, to all the way to consumer devices and IoT devices. For going from wearable devices, low power battery devices, of course, including the smart speakers, which we just talked earlier about, the huge growth you saw this year, as well as connected homes, smart cities in enterprise and professional. Now, what's driving this is, what's the foundation of this is the requirements for rich and robust natural interfaces, or also known as human-machine interfaces, or we call it natural interface because it could be other than interfaces between machine and machine as well. The tools and infrastructure to support this are also very required, very relevant and important. And the consortiums like tinyML Foundation as an organization, the ML Commons, which we are very deeply involved with all of these consortiums to help grow the tinyML community. And beyond that, benchmarks are very critical. We've been part of this ML-Perf benchmarks, working with the ML Commons teams. In the Tiny group, one of our founders is chairing and helping to come up with the right benchmarks for wake words, to visual wake words, to gesture, anomaly, etc. So these are just the foundational things that are helping to build this industry, which is predicted to grow to billions and close to 30-40 billion units per year shipped. We think actually it's probably even it's not far from the truth. The reason being, if you look at where natural interfaces started with keyboard, of just going back a few 30-40 years, keyboard was the interface. Even now we use it. It's we ship PCs about 150 million units a year. Then if you move into the next sort of the mouse, that increased amount of with Windows and the interfaces, that increased to about 500. It was a 3x that. And then we came to the touch screen with the introduction about a decade plus ago, with even before that, but really where it got traction with the with the touch screen, and you have now about 1.5 billion units per year. We think with natural interface, that is the human machine interface, that is what we are seeing. That's where the growth is going to be 3x or more if you continue on that trend. So we cover, you have to think about all the opportunities there, from sensors, which we talked about, for event detection, the wake words, which you heard about from a couple of earlier speakers, as well as commands, voice and speech, and then vision. So I think as this natural interfaces grow, the amount of opportunities for all these devices, which I talk about, are going to grow. Now, what are the requirements for these devices? What do these devices have to be to mean successful deployment of these devices? First of all, they have to be energy efficient, because they're going to be right at the edge, right at the human-machine interface, things which are always on. So energy efficiency is what we also looked at when we first started. Latency is very fast. I mean, you can't have there's not much time for the device to respond. You have to respond quickly, so it cannot go to the cloud, come back every time. It needs to know what you're thinking or saying or doing. Reliability, because it has to function with a very low false accepts, false rejects. Cannot make mistakes, and reliable performance. And most important, last but not least, is privacy. That means all of this data that we see in the day-to-day are all data that we want to keep ourselves, and privacy, and a lot of people have talked about it. So, but these four elements are really what are going to critically make a difference for whether your product, tinyML product, is going to be successful or not. Now, the reason how we looked at it as, and generally this is true for anybody, is that the always-on domain is where all the data is. 95% of all data generated in sensors is to be processed locally. And that's where we look at it. Has to be low power because of all amount of data, and it has to confirm all the things I mentioned previously: latency, power, energy efficiency, reliability, and privacy. For all this, it has to be done locally at the always-on domain in low power. Now, after you can wake up the high power domain, like the application processor, which runs an operating system or some other bigger applications, and then connect to the cloud, and then a radio to various mechanisms to go and connect from there to some other outside world. So where do Syntiant where do Syntiant's products fall into in this domain? we started, as I mentioned, the first generation was 4 years ago, was in speech, your device can listen. So it's speech AI, NDP 100, we call that then. And that's based on the first generation cores that we developed. Now, beyond that, with 120, which we launched earlier this year, has speech and sensing. So you could do accelerometer, or any other kind of sensor integration along with speech. So it could be it's a concurrent neural engine. It's a much more powerful, larger neural networks. So we consistently increase the size of the network and what we can do inside these chips, but continuing to keep the power budget low to be in the microwatt range. So then we have introduced the 200 just a few months ago, a couple of months ago, which is including voice. So voice, now we do voice, we do speech, and we have sensors integration. So all of these devices are finding large application space from across voice, I mentioned, acoustic event detection, like if you want to detect glass breaking, or I will show a video quickly, or baby crying, or any of these acoustic event detection, motion detection, because a person, you can do it by different ways. We just announced one relationship, our collaboration with a company called Elliptic Labs, where we're doing ultrasound-based person detection inside the room, as well as other sensors integration as well. So the application space for our applications are across from mobile, I mentioned earlier, to all these different IoT devices, from wearables to automobiles, and in an always-on domain. So why do we need more neural? I said we kept increasing the neural capacity, and I wanted to point out a couple of interesting publicly presented information from actually, the first one on the left side there is by Pete Warden, who's Daniel's, who spoke earlier. Both of them wrote a book together called tinyML, and he's also on the tinyML board. So just a few years ago, not even last couple of years ago, he had presented this at the Lindley Fall Conference, where he mentioned that tinyML is, has to be very low power, which is correct, sub-milliwatt. But it's low fidelity, you have resource constraints, so definitely you're not going to be able to do too much. So you leave the first gateway to a cascade process, where you do that, and then hundreds of milliwatts to run it on the CPU, and then cloud processing for some. So just what you do in an integrating in tinyML into a larger system, you will need to do all of these things. This could be for voice, could be for anything, but just as an example, you mentioned this. So if you look at what somebody else, like Alex Grunstein also has published, and this is on YouTube, you can go find a video. He says the batteries that are needed for mobile phones, for example, he's actually the founder of, he started the Google Hot Word, OK and Hey Google. He developed it from scratch, and that's pretty much one of his. He's founder of that group and the project, and what billions of devices today do. And he has written and he has said that to run a hot word on a CPU is going to take you tens and hundreds of milliamps. So, and then follows on to say the complexity of having this always-on DSP to do, sub-milliwatt, just like what even Pete had mentioned. And then you have to have this other additional keyword spotter, which will then consume tens and hundreds of milliwatts. Now, beyond that, you want speaker verification, and then go to the cloud, to verify that even more to reduce the false reject rates. So this means that your tinyML device, if it is restricted in, constrained in memory, constrained in processing power or accelerator, neural capacity is low, then you will have to rely on somebody else to verify what you did. And that is what we're trying to avoid. So what we did, and what I would like to show you here, is that you can actually run the entire, if you had more and more neural, you could run all of that confirming high fidelity model that's running at hundreds of milliwatts, for example, in our device, and it's possible to do it in half a milliamp of power compared to the 10 to 100 milliamps that was the norm in most of these devices. And this is today, we believe, the lowest power implementation of OK Google in the world. So here's a quick video of that. Let me go to the processor. Let me go to the next one. Sorry. Okay, let's start this. This is the confirming model. There are two. The cascade is not needed.
Here's a demo of the NDP-120 running the OK Google fine model, the confirming strength hot word engine. So you can see we're tracking the average power, and this is on the NDP-120 core supply, just burning over 430 microwatts, including the audio codec and the full hot word detection.
So that just shows you how we can run at extremely low power the Google hot word. Now you can do concurrently. Not only that, you can also do some additional things in this without any extra.
With this video, I want to show you one of the really cool features out of the NDP-120, which is Syntiant's newest neural decision processor based on the Syntiant Core 2. The idea is that we've invested an enormous amount of time in our networks and have our silicon in the field Syntiant Core 1. What we've been able to do with Syntiant Core 2 is roll in 25x the compute, roll in much more powerful neural decision processor that supports CNNs, RNNs, and all these toolkits that an ML scientist is using. But we haven't given up the ability to just directly load our Syntiant Core 1 models. So what I'm going to show you in the background, we're actually loading two of our NDP 100 models. We have our Alexa wake word, and we have our glass break detection. So what's neat about these is there's two completely independent models listening to the same audio stream, and they're actually running at different frame rates. So we're booting up the device, and what I'll show you, we're going to listen live to the microphone. You're going to see the joint solution looking for the wake word Alexa and also glass. So you can see the power is right around 300 microwatts. I can say the word Alexa. Alexa. At the same time, I'm running the glass break model. So you can see the models concurrently are looking for both of these features. So I have the sample tank, I have the concurrence, and I have the ability to run multiple networks on this device without actually having to worry about joint training.
So as you can see, we are able to run quite a lot of very robust model that doesn't need another network, another chip to confirm what it did, or even send it to the cloud for that matter. Plus has lots more capacity to do additional things like speaker verification or sound detection like we showed, or gesture even. So how do we do that? So the secret to this is the network inside. So we put a large neural network inside the NDP-120. It's still a small device because of the architecture of how it was compact and being able to do at memory compute. That I think has been mentioned a few times, that allows you to compute, do the computation, and keep the memory without having to send the data back and forth. So that kind of a new way of doing your compute helps you to not transfer memory back and forth and therefore consume a lot more power consumption. So that's one of the tricks. The other is we are able to handle from 1 to 4 and 8-bit weights. So we can be interchangeably in our network, between layers, we can go to different levels of resolution. All of this allows the designer of the modeler to have much more flexibility. And I will give you a little bit more idea later on that we can actually not only do this on device, but you don't need a separate compiler to do this. So that affects effectively ability to add all of this neural compute inside the device, allows you to provide this level of flexibility and compute that you can use for a lot of these functions that you have. So this was our Syntiant Core 2 based architecture, and the next device, which adds vision, uses the similar Syntiant Core 2 architecture, but adds the vision interfaces and other image interfaces to be able to do the same, including audio, speech, and sensing. So that's the idea, that you can do all these things in parallel. So as I mentioned, if you look at this kind of large network ability to handle it, all the different types of neural network ML scientists would need, like CNNs, RNNs, GRU, all of these available toolkit of networks are available in this chip. Now, that mentioned was at memory compute. The other one is a sustained is utilization. So number of times you will see tops per watt and all these marketing numbers, but if you then go dig into what kind of utilization is, what's the efficiency, you will see a lot of them are not 100% or even 50% efficient. So what we have, our architecture is very, I would say closer to 95% efficient in terms of its achieving its utilization. So that's the kind of architecture that allows us to completely utilize the neural network, the capacity inside the chip. It allows maximum usage of operations and then reduces the power and gives you much more capacity. And just as in a comparison point, compared to an A53, the Syntiant Core 2 architecture we have shown running a mobile net, V1, an in-tate network was about a 30x in terms of its inference per million cycles, or the inference, and then power consumption was another 100x in terms of its energy efficiency. So just as a what does that give for you? If you think of what I couldn't do with a A53, a car battery inside an automobile. This is for the 200, which is a vision thing. Inside a cabin, I can have a battery running, doing always on vision, and let it run for a year, versus say an A53 based controller would die within 4 hours. So what are the other tools, or what are the other things we need to make this edge AI a reality, or increasing the capacity, is giving the modelers the capability to explore that entire design space and the tools to estimate the power, the latency, the memory utilization, and optimizing all of these in the hyperparameter search and combining it with the result, showing the results in power and latency and memory. So all of this, we do not need a separate compiler to generate the neural network for NDP. This neural designer lets you design the model that runs on the chip directly. And this gives you, as you run and you modify, you can see the power consumption as well. Like, for example, it says how many cycles it took to run this layer, what was the energy consumed, how many parameters were used, and which bank of memory it used, and all of this on the chip without actually running it on device. You can do it all on the Syntiant Neural Designer. And lastly, I think, and this was mentioned a few times, we have built production grade models, and one of the key or the secrets behind that is the data. So we take raw data, and we generate very high quality data that actually can result in very good quality models that can run on the chip. So I think that was mentioned earlier by Daniel also, that it really is very important to have good high quality data that can actually run. And so our tools not only are for training, but it's an end-to-end system that allows you to acquire the data, and not only acquire the data, clean the data, and also generate more data. So synthetic generation of data using AI techniques, and validation of the data, and auto alignment, labeling of the data. Plus, we have humans in the loop to verify and quality of QoS, that's quality of the data. But in general, our tools allow data labeling along with alignment and generation. So I think these are all these three things, if you look at it, neural compute, 100x the efficiency, 30x the throughput, and very small because of the architecture. Combine that with the training that you can do with the data that you generate, and you can and the data platform. So we provide now end-to-end solution that is actually what is needed for to deploy tinyML at scale because of the amount of data that you will have, amount of training you have to do, and to keep the power and get the best efficiency out of the end product. So all in all, I think, again, going back to what I'm saying is in the end, the natural interface that we want are, we want the data to be private. We want the cloud to be around us and not the data to be sent out somewhere else. We want it to be fast, responsive, low latency, and energy efficient. I think that's what having more AI engines, more neural processing right on device allows you to do. I hope that was explanatory. I was trying to be as concise as possible today. Hope you can ask me some questions if you have any. And if you have any questions, my email is up here. You can send me an email.
Yeah, we're actually getting some questions in the Q&A window. Are you concluding that a smaller capacity ARM Cortex MCU with a higher capacity NPU that can run CNNs or RNNs delivers the best performance in a constrained system?
Yes, we believe moving to neural accelerators is the way to have the best performance and power and all the things that I was showing you. This is necessary. This is just what is needed in edge AI, in tinyML systems. Having Harvard architecture or whatever, Manhattan, just fetching data, fetching instructions, and executing them serially, or even in multi-scalar or whatever. But what happens is the power goes up, or you're trying to balance, or you're trying to optimize for different things. And in fact, Daniel also mentioned just before me how you have to do unnatural things to get your model smaller, or quantization. You lose accuracy, and then you're spending a lot of time trying to make it work. This is the best way. This is the way to go.
Thank you. So if our audience has any other questions, please raise them in the Q&A window. Evgeny, I saw you have your hand raised. Do you have any questions?
Yes, as usual, a tough one. But before that, Mallik, great presentation, really amazing progress. I mean, you guys have 3 products now in a very short time, given all the constraints and all the software related work. Really impressive, and congratulations.
Thank you.
Now, my question is, on page 12, you had a comparison of your cores to 2 different ones, and then you compare it to, I believe, to A7. And I was wondering, how does this number going to look like if you compare it to like U55 or U65, which will be more like apples to apples rather than A53, because A53 is like a really high performance ARM cores, right? And
yeah, I mean, we're not saying that there is, we have yet. I think we've yet to see the proof in the pudding, so to speak, right? So it's definitely a lot of people everybody's trying to catch up to what we have already shown. in the tinyML space. Obviously, these are not, this is not something that we didn't know, right? I mean, a few years ago, I knew that you had to build, AI engines, neural processors were being developed even before Syntiant, right? But the question really was, were they efficient? Were they looking at, would you be able to put it all in a device and make it, architecturally, would you be able to combine, bring the, so can you bring so the constraints were not there. Earlier, you would develop this, you would have DDR and PCIe, or, just bring all the data in, and, power consumption was high and nobody cared, right? Because you're running it in the cloud. But now, yes, okay, ARM is, doing it, but that's evolution, right? I mean, everybody, but all I'm saying is that we have done it in a way that is what makes sense, right?
I totally agree with your architecture. That's why I'm asking, like, if you compare it to U55 or U65, which are also kind of microcontroller-based type of architectures of ARM.
Yeah, I'm sure it will come to that. We'll compare it when it's available. I think we haven't seen any devices yet with it, so that's why we have not compared it. But when it is available, we have done internal benchmarking. We have ARM IP, right? So we talk to ARM and we get down and look at it. But we believe that what we have done is order of magnitude better.
I agree with this. I'm just wondering about the numbers.
No, I know, even compared to that.
Yeah, so I think like what Odin mentioned earlier, that Hymix has now some processors with.
Yes, I believe they will.
And then Elif announced at the Dev Summit, ARM Dev Summit. I'm just wondering, is it going to be like 10x, 5x, 3x? Just because, philosophically, it's kind of similar approach, but of course, you did things in your own way, which is, I think, is pretty cool.
Yeah. I think it's again, it comes down to whether you want to how closely are your architectures, right? You're architecting it to the application, right? Yep. So if you look at the use cases, they're very specific. It's not very generic. I'm not doing something and just hoping somebody will come. I'm developing my architecture to my use cases, right? So
totally agree. Okay, thank you, Mallik.
Yeah, for sure.
Cool. One more question from our audience. Are you collaborating with Google on the video doorbells or cameras, like a Google Nest series?
I cannot disclose my customer base, but we are, as I said, and we have announced publicly that we work very closely with Google.
Thank you.
If you have any questions, please feel free to contact me or go to our website.
I also want to extend our gratitude to all the tinyML strategic sponsors who made this event possible. At the executive sponsorship level, we have ARM, my old employer, who provides the software and the hardware foundation, tinyML. Edge Impulse is the tinyML platform for all developers. Qualcomm advances AI research to make efficient AI ubiquitous. Syntiant offers end-to-end deep learning solutions for tinyML and Edge AI. At the Platinum sponsorship level, we have Reality AI adds advanced sensing to your product with Edge AI and tinyML. Renesas, who has big ideas for every space. With our golden sponsors, Latent AI develops adaptive AI for the intelligent edge. Maxim Integrated, who is now part of Analog Devices, enables edge intelligence. Seed Studio, they are the IoT hardware enabler. tinyML builds smart IoT sensor devices from data. Synsense builds sensing and inference hardware for ultra-low power devices. We will have some special partner sessions in the next few days, led by the sponsors we just introduced. At the silver sponsors level, we have Aeon Devices, Deep Light, AMSA Vision Sense, GreenWaves Technology, Gravity, HOTG, Imagine Mob, Kixel, Rexin, and SAP.